Before we talk about harmonic functions, it's helpful to review the ddz and ddz bar operations. So these were introduced in a homework. But ddz is given by 1/2 partial with respect to x minus I times the partial with respect to y. And ddz bar is the same thing except with a sign difference. And this is an efficient way to write the Cauchy-Riemann equations and the complex derivative. So here are some basic facts about these operations. If we write f as u plus iv, then df dz bar equals 0 if and only if the Cauchy-Riemann equations hold. And that's just by writing everything out. So here are some of the details. Du plus iv dz bar will be equal to 1/2 ux plus iuy plus I times Vx plus Ivy. And if we look carefully here, we see that the real part is Ux minus Vy, and the imaginary part is Uy plus Vx. And so when those two things are zeros, that's exactly the Cauchy-Riemann equations. On the other hand, if f is holomorphic, then this ddz gives you the complex derivative, and that's just because we already know that if f is holomorphic, then df dx gives me the complex derivative, while minus I df dy is the complex derivative, and then ddz is the average of these two. And the final thing to point out is that if you do the two of these in a row, you actually get 1/4 times the Laplacian, which is the second derivative with respect to x and the second derivative with respect to y added together. And that basically works out because these derivative operations commute, and you get basically a formula analogous to z times z bar equals modulus of z squared. And this is the connection to harmonic functions. Okay, so what are harmonic functions? A function u from an open set into the real numbers or the complex numbers. We'll usually talk about into the real numbers. Let u be C2, so we want to assume we have second order partial derivatives existing and being continuous. We'll say u is harmonic if its Laplacian equals 0. Now here are some basic facts. Holomorphic functions are harmonic, and that's just over here because when I take the Laplacian, we can view it as taking the ddz bar first, and if f is holomorphic, then its ddz bar derivative is 0, so you don't even need to apply the second half of it to see that the Laplacian of a holomorphic function is 0. On the other hand, if I have a harmonic function, you get that its dz derivative is holomorphic, and that's because, well, you can switch the order of these two, and because you can switch the order of the derivatives with respect to x and y. And so du dz, if I apply d dz bar to that, I get 0 because u is harmonic, but then that says that this part satisfies the Cauchy-Riemann equations, which by our earlier theorem shows that this derivative here is actually holomorphic. Okay, and an important notion related to harmonic functions in the complex plane is harmonic conjugates. So if I have a harmonic function, we say that v is a harmonic conjugate of u if u plus iv is holomorphic. So if f equals to u plus iv is holomorphic. And we're trying to represent u as the real part of a holomorphic function. And you can see from our previous slides in the geometric interpretation of the Cauchy-Riemann equations that u and v with this relationship have special geometric properties, so their level sets will be orthogonal and so forth. Okay, so when do we have harmonic conjugates? If I have a harmonic function on a domain u, then u has a harmonic conjugate on u if and only if this du dz has a complex antiderivative on u. So why is that? This is pretty straightforward. Here's the proof. Let's see how it goes. For the forward direction, if u has a harmonic conjugate, then that means there's a v, so that u plus iv is holomorphic here. And I can take the du dz derivative here, and it just comes out to be 1/2 ux minus I uy. But by the Cauchy-Riemann equations, I can write it as ux plus I vx, and this is just 1/2 the complex derivative of f. And this has 1/2 f as an antiderivative, no big deal. For the converse, suppose we found a complex antiderivative of this holomorphic function, du dz, and we have to do a little playing around with this, but basically capital F is what we want. So to see that, set u tilde to be the 2 times the real part of capital F, so f plus f bar. And now if we take the dz derivative of this, I'll get the complex derivative of f, and when I take df bar dz, that will be 0 because it's the conjugate of taking df dz bar. So for this part, the contribution is just the complex derivative, and then here I just have du dz, so this is 0. But for this real valued object, I get that d dz, I'll just have these x derivatives in the real part and these y derivatives in the imaginary part, and this is identically 0. So this difference has partial derivative with respect to x and partial derivative with respect to y, both identically 0. So that means u tilde minus u has to be constant because we're assuming we're on a domain, so it's connected. So this difference is constant, and then what we get out of this is that the real part of 2 times capital F minus this constant gives me little u. Why is that? So I have f plus f bar minus c here, but f plus f bar was u tilde and u tilde minus c is equal to the harmonic function u. So we've constructed u as the real part of a holomorphic function, and that means it has a harmonic conjugate. Okay, so this was just some definitions and basic notions related to harmonic functions in the plane. We haven't gone into the motivations, but harmonic functions are solutions of Laplace's equation, which is one of the most important PDEs related to heat at a steady state. In any case, we may talk about the motivations in more depth later, but now we're going to talk about some deeper properties of harmonic functions that we can deduce from some stuff we've already proven about analytic functions.